Hello, everyone. If you see my channel for the first time, welcome. Today, we're going to discuss the most challenging math competition in the world, the International Math Olympiad. It consists of 2 days, and you're given 3 questions to solve in 4.5 hours. Day 1 of IMO 2025 happens in Australia today, the 15th of July. And yeah, I'm going to walk you through the first problem, the easiest problem, on the hardest competition in the world. And we're going to make it easy. So let's jump into the problem statement. What also I'll say before we start the video, the main aim of this channel is not to tell you the solutions. My main aim is to tell you how to think the best and the most efficient way. And the way I do that is I tell you how to think correctly and how to think incorrectly in different problems, and explain my personal approach to different questions in hopes that it might help you to develop your thinking in questions that you get. So let's start with the question. A line in the plane is called sunny if it is not parallel to any of the x-axis, the y-axis, or the line x plus y equals 0. So we're working on a coordinate plane, which is essentially something like this. You have a y-axis here, you have the x-axis here. And a line is called sunny if it's not parallel to the x-axis, so this direction, y-axis, or the line x plus y equals 0, which is this line. Okay. Now we have n more than equal to 3 is an integer, and we need to determine all non-negative integers k such that there exist n distinct lines in the plane satisfying both of the following. First, we want for all positive integers a and b with a plus b less than n plus 1, the point AB needs to lie on at least one of the lines, and exactly k of the n lines are shown. So first of all, let's understand what does this statement mean. In order to solve any question, you need to look at the statements that you're given and determine which ones do you want to rephrase in some way and which statements do you want to keep. If you're interested in that, I have 2 videos on geometry specifically called Good Point, Bad Point Method, and another one is called The Key to Solving All Problems. So I think these 2 videos are one of the best so far on my channel, so I really recommend you to have a look at them. Okay, so let's draw the coordinate plane. These are in our 2 axes. We have the y-axis on the top and x-axis on the bottom. So the statement that we want all points a and b such that a plus b is less than or equal to n plus 1, essentially what that means is that you take these points. So a and b were non-negative integers. So essentially what is being said is you need to take a look at this figure. So it's like a triangle like this. And we look at the points in this lattice. And these are essentially all the points for such that a plus b is less than n plus 1 and a and b are positive integers, where this point is has the coordinate of n plus n, and this point has the coordinate of 1. This is 1, 1, and then this is n as well. Okay. And what we also want is we want to basically cover all these points with n lines such that exactly k of them are sunny. So for the more advanced people, the way you start thinking of these questions is we don't know the answer yet, but since the answer might vary due to our variables, which is n, the answer, so all non-negative k, might be different. So essentially what we want to see is we want to guess the answer by just looking at small cases. So for example, we start from n equals 3. So we start from n equals 3. So the first thing you want to always start and do is try to look at small cases. So for n equals 3, if we have a lattice like this, we want to find the answer, we want to determine all integers k that are non-negative, such that there are n distinct lines, and we want k of them to be sunny. So obviously, we can achieve k equals 0 by drawing 3 parallel lines. So k equals 0 is always possible. We can also achieve k equals 1 by something like this, because this line is not sunny and the other two are sunny. This line is sunny and the other two are not sunny. And now we want to know if we can do 2 lines. And here we can manually check that it is actually impossible to get it in with 2 like sunny lines. The reason behind that is a sunny line, it can pass through at most 2 points. And if there are 2 sunny lines, if there's 2 sunny lines, the only possible way to get a sunny line in this configuration is this line, or this line. And it so turns out that if you choose any 2 of them, the other one should be automatic. Or if you don't choose 2, you have to choose a 3 in a row. So if you don't have 2 sunny lines that both have 2 points lying on them, there needs to be a line with 3 points. So it's either this line, and then it's impossible to cover this with 2 sunny lines, or this one, and similar story here. So k equals 2 is impossible, and for k equals 3, we already showed the example. So the example is this, and this. So these are not sunny lines. The sunny lines are the ones that are parallel to this, or this. Okay, so we determine our answer for n equals 3. And in most of the cases, you want to build up. So what you then want to do is you want to look at the case n equals 4, n equals 5, n equals 6, and try to build a hypothesis, a prediction for what the answer is. And what happens when you try to build and find answers for n equals 4, n equals 5, n equals 6, and n equals 7 is that you can't, no matter how long you try, you won't be able to get anything except for k equals 0, 1, and 3. And besides that, you always can construct k equals 0, 1, and 3. And the reason is you can draw always these lines like this. And then when you hit n equals 3, you do the same thing here, like this, which includes n lines, and you always get 0, 1, 3, or like this, or like this, doesn't matter. So you can get all the same 0, 1, 3 answers just from this. Okay, so we confirmed that our answer might be a constant, so our answer might be 0, 1, and 3. And now we try to think. So now we're a bit stuck, and we are trying to show that in order to get, you can't get 2 or 4 or 5 or more lines that are sunny. Okay, and the way you think about this is you don't try to test something, or you don't go to like asking questions and trying to brute force your way into the question. That's what I always preach. I don't preach trying to solve the question immediately by trying different methods, because if, say, I don't know, pigeonhole principle. If you try pigeonhole principle without any evidence that it will work, you might waste a lot of time, which is the most precious attribute you have in an Olympiad. So what you want to do instead in questions when you're stuck. And even if you're not stuck, before you jump into proof, and after like looking at small cases maybe, what you should do is ask yourself a couple of questions, and these questions should be oriented in another way, not in a brute force way. And the thing I'm talking about is an interpretation of a problem rather than a maths problem. Interpret as a puzzle and try to solve this puzzle. So you have a lot of clues in the problem on what to do. So the statements you get and the conditions of the problem you get, consider them like clues to solving a puzzle. And what you need to do, instead of like trying different methods or it's the same as when you solve a riddle. You don't just go for an answer. You look at different clues and you try to work it up together. So here you need to look at the clues, try to get something from them, and then conclude which method is the most suitable to use. So now let's think. If our answer is 0, 1, and 3, that's the clue that we kind of get. We guess that our answers are 0, 1, and 3. So our next question is, how can we show that? How can we show that the answers are 0, 1, and 3? Well, either there is a specific formula that says, okay, if you have more than this amount of sunny lines, we bound something and it doesn't work. So you bound the amount of points they cover or something else, and you bound it all together, and you get that you can't get more than 3 sunny lines, never. And for 2 sunny lines, you don't know what to do. So that's another question. So there must be a reasoning why 2 sunny lines don't work and 1 and 3 work. So that's one approach. But again, the nuance that 2 works and 1 and 3 works tells us that that's probably not the right way to go. Now, the other way we can go is called induction. And the reason induction is suitable here is because you do have the same answer always. So if the answer is maintained throughout all the n, so from n to n plus 1 to n plus 2 to n plus 3, and if the answer is the same, there is a good chance that induction might work. And a lot of people know induction, and a lot of people may jump straight ahead into induction in this question, and it might work out, I agree. But it's the same as teaching a wrong technique to a beginner, and it might work out in some cases, but if you don't perfect your technique later, you're going to get caught and you're going to be punished in fighting or in anything else, in cooking as well. If you have a basic mistake, you need to fix it as quick as you can. And jumping straight into induction is a basic mistake. Sometimes it does work out, like in this case. It might work out for you. But just for the sake of not making stupid mistakes, never jump to induction straight away. Look at small cases, build a hypothesis, try to find for clues. If induction is suitable, if you see that it might work out. So if you see that it might work out in this question, go for it. But if you have nothing to do and you think, okay, let's just try induction, that's not the way you should solve a math problem. That's what I'm basically telling you. So let's go back to the question. We want to think about induction. So induction, basically what it does, we go from n equals n to n equals n plus 1, essentially. So we add these lines, these points, and now we have n plus 1 lines. And we assume that in order to cover all the blue points, we can use only 0, 1, or 3 sunny lines. Okay, so we're trying to simplify and break down our question from n plus 1, which is the new side of the right-angled triangle. And we're trying to break it back into n. So induction is never about going from n to n plus 1. It's simplifying from n plus 1 to n. That's a nuance that you might not understand right now, but especially when you solve questions from graph theory, you can make a lot of stupid mistakes by just considering moving up rather than moving down. So induction is not moving up from n to n plus 1. It's moving down from n plus 1 to n minus 1, and so on to 1. And for 1, you show. Okay, so right now we have these lines, these red points, and we're trying to simplify it back. So we try to simplify the n plus 1 right angle triangle into the n1. And what we notice is that when you do the small cases, there's one common thing that unites all of them. So it's always like a big line with n points. And since we have like n times n plus 1 over 2 points, and we need to cover them in n lines, that means that some lines must be very big in order to compensate, because at the end you don't have a lot of points. So that's what you notice when you start to analyze the question. So, okay, and now we can build a hypothesis and try to show that since in all our previous cases there was a big line, right? And when you cut off a big line like this, you basically get the same n by n triangle here. If you cut off this big line, you get the same n by n triangle here. And if you cut off this, you also get an n by n right angle triangle. So this would be very nice. And we would essentially finish the problem if we showed that there must be a line that passes through two vertices of the big triangle, because then we would say that we are left with a n by n triangle, and for that we know that by induction and blah 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 we're done. So now our main focus is try to show that it must be a big side. But again, this hypothesis, it doesn't come from the air. We don't assume it from nothing. We don't try to show nothing. We look at the clues, and the clues are small cases. We look at different ways we work with these small cases, and we build hypotheses. That's how maths should work. You shouldn't just jump into conclusions. Your work should be absolutely logical, and it should also be a bit like playful. So you shouldn't be like, okay, we do this, then this, then this, then this. It should be more playful. It should be like solving a puzzle. It should be trying this, trying that. Okay, what's common? What's different? It should be about exploring the question. So now let's try to show. So after we explore the question, now we have the practical maths, basically. We show, we prove something. But proving is not the hardest part in maths. The hardest part in maths is actually building the hypothesis to prove. And that's where everyone gets stuck. So please pay attention to what I said. It's really, really important. Now, we do want to show that there's a big line that passes through n plus 1 points in this big n plus 1 by n plus 1 triangle. How can we show that? Well, essentially, you can test different methods here. So you can assume that there's no such big line. And what that means is that if we look at all the red points, they need to be starts of different n lines. And because we have n, we already have n different lines, right? So all these n plus 1 starts, this start 1, start 2, these starting points, and start n plus 1, all these n plus 1 points, they need to, if there's at least 2 points that are connected by one line, then there's like a big side already. So we're done. So now what we have is that all these S1, S2, and so on, Sn plus 1, they are starts for different lines. So essentially from here there's one line, from here there's another line, and they all go like in this direction. And now we want to cover the whole of this thing in n plus 1 lines that start in different points. But again, all these points, this, they also have different starts for the same reason. So this means that S1, it needs to be going somewhere here. And then we know that this point, well, essentially you have a lot of stuff that you can try. But at the end of the day, you kind of work around the boundary of the big triangle. And we see that each line that passes through this point, through here, and through here, it crosses, if it doesn't pass through all the lines on the boundary, so if it doesn't contain a big side, each line start on the triangle, on the boundary, or it then leaves on the boundary. So essentially what we're saying is that each point on the boundary needs to be included in a line. And if we calculate the amount of these points, it's actually 3n minus 3 points that are on the boundary. So red points, these ones, and then these points as well. There are 3n minus 3 of them. And when we conclude that, we do know that each line has a different start, different finish. And if each point has a different start and different finish, then each point, there must be at least this amount of lines, which is a contradiction for n more than equal to 3. So yes, and in this way, you can actually show the problem instead of just speculating and jumping into random conclusions. Because if we have different starts of lines, 3n minus 3 divided by 2 is greater than, well, if there's 3, it's just 3n, if there's n plus 1 by n plus 1 triangle. So 3n plus 2 is bigger than n plus 1. And that's the amount of lines we needed, which drives the contradiction to why it is impossible to cover the whole plane in n plus 1 lines if there's not a big line that passes through either side of the triangle, which finishes our proof by induction. So thank you everyone for watching, and I hope